Alright, fine. So can you see my screen? Please guys, speak up right now. If you do
Yes,
not
sir.
Yes,
speak,
sir.
what will happen actually if I somehow disconnect from you? I cannot trace you actually. Please speak up. Is there anything actually whether you are can hear me properly or not, whether you can see my screen properly or not? Please someone voluntarily do that one. Otherwise we will be in difficult position. Fine. So I think you are talking about that. I have finished that parallel axis theorem and the perpendicular axis theorem in your section, right?
Yes, sir.
Yes, sir.
Still someone knocking. All right. So I think I also talk about that rotational kinetic energy in your section. Did I talk at rotational kinetic energy? So rotational kinetic energy means let's say you have uh, three object is connected by three massless rod, and let's say I'm going to rotate that system about this axis. So let's say this is my rotational axis. I'm going to rotate that system about that axis. In that case, this system going to rotate with a different speed actually, or you can say the linear speed would be different for different object. This one would be has a linear speed toward that direction. Let's say with a v1, this system will have a linear speed toward that direction with v2, and this system will be rotating that direction with a linear speed v3. And I also consider that this one has a distance from rotational axis r1. Let's say this is r2 and let's say this is r3. If I rotate that system with a angular velocity omega, then translational kinetic energy, or simply the kinetic energy, will be probably right half of m1 v1 square plus half of m2 vt square plus half of m3 v3 square, right? This would be the kinetic energy of this system, right? Am I right? For these three
Yes, sir.
objects. Fine, then I know there is a relation between that linear kinetic energy to the translational kinetic energy, right? So linear kinetic energy actually we define V actually omega r. That is the relation between that linear speed to the angular speed, right? Since in this case actually this omega is fixed, that's means we are rotating the system with a constant angular velocity. That's why omega would be fixed. Since the r difference, that's why I can say that v1 should be omega into r1 and v2 should be omega into r2 and v3 would be omega into r3, right? I'm going to replace those things over
Yes,
here.
sir.
So then I'm supposed to write half of m1 v1 should be omega square r1 square plus half of m2 omega square r2 square plus half of m3 omega square r3 square. From here right now I can factor out half of omega square, because this is common in every portion or of the parameter over here. Then I can also write down this thing in terms of summation notation. Actually I can write I1 2 3, this should be mi ri square. Can you write this one? Because look at this, if I plug in index I equal to 1, first thing would be m1 r square, plus when I plug in I equal to 2, this should be m2 r2 square, and when I plug in I equal to 3, it should be m3 i3 square. So that's when I can extend this one according to this summation notation. You will find out the same thing, that thing. So fine, now I am going to rewrite this equation. Can you tell me what is this? Can anyone give me?
I.
It's a moment of inertia, right? Which is I. So that's when I can write this moment of inertia half of I omega square. This is known as actually that rotational kinetic energy. So that's when the system is rotate, only the rotate, then your kinetic energy would be a half of I omega square, where I is the moment of inertia of that system. And when system has only this motion, we say that system is rotating, or this is called the rotating system. When the system has only half of I omega square, system have only the rotational motion. When the system has only half of mv square, it is called the translational system or translational motion, or sometimes we say the linear motion. Translational motion or system. And when the system has both type of kinetic energy, that's mean half of mv square plus half of I omega square, then we say that the system is actually the rolling motion, or sometimes we say actually that pure rolling motion. Alright, so you can give me some examples. So let's say only rotatory motion would be basically, you can say that the motion of a ceiling fan, because that ceiling fan only rotating about its axis, right? But its center of mass is not actually changing its position. It's rotating about its center of rotation actually. So that's why the motion of a ceiling fan would be only rotational motion. Sometimes you will find that the system has only translational motion. Let's say when you release a block from inclined plane, let's say if I release a block only from inclined plane, it has only the translational motion when it's moving to the downward direction. But the motion of a let's say wheel of a car, it has both type of motion, which is rotational as well as translational motion. It has both type of motion, because this let's say this is a wheel, it is rotating about on axis, and it is also, let's say, at angular velocity omega, and its center of mass is also moving to the downward with a speed v. That's why this type of motion is known as actually that purely rolling motion, when the system has both type of rotational motion and also translational motion. This is known actually the pure rolling motion. The motion of a car or the motion of a car wheel is actually the pure rolling motion, because it has rotational and translational motion. Alright, do you understand?
Yes, sir.
Let's say I have these two identical objects with the same mass m, and I release that system from a identical inclined plane also, which is actually that h, if I release, and it's a frictional, since the material are same, the friction will be the same on both two objects actually. So if I release these two objects at a time, can you tell me which object is going to be the come down first?
প্রথমটা
Block. Is there any other opinion?
হ্যাঁ জি স্যার
Is there any other opinion over here?
স্যার ব্লক হবে
I can hear you.
ব্লক
guys.
হবে
Block will come down first. All right, let's see that actually it's not the block, is this sphere, or you can say the solid sphere is going to be the down, or disc, this is going to be the downward first. Why? I'm going to show you. Say, let's say this is a block and this is a wheel of a car. So it will be only let's say if you consider the total initial energy equal to total final energy for both case, then only that potential energy mgh is going to be the convert to the kinetic energy over here, right? When it's come down first, come down, there's that surface or the ground. Then for the block, it has only half of, it's a capital M, it should be half of mv square, right? But for this wheel, it has two type of motion actually. mgh must be converted to the half of mv square plus half of I omega square, right? Because it has both type of motion, rotational and also translational motion. So that means whatever the energy it has, it will be converted or it will be utilized to rotate the system as well as to go to the downward direction. So that means the total potential energy must be converted to the translational motion as well as rotational motion. So that's why this energy will be divided in the two portions. Whereas for the block, the total potential energy only convert to the translational motion. So that's when translational kinetic energy over here. That's why the V is going to be the higher than this case. That's why this block will come down first. Do you understand? So that's why if I release
yes sir
two identical objects which has the same mass, and if we release from a same height or same identical inclined plane, in that case this block will be come down first because it has only translational motion. That means whatever the energy, it will be totally converted to that translational kinetic energy, not for that rotational. Because in the case of disc or solid sphere, those part, this potential energy is going to be divided in the two portions, one for rotational part, another for translational part. So that's why definitely if you have that 5 joule is totally going to be converted to the over here for the B, but in this case the 5 joule, some portion will be go for over here and some portion goes over here. So that's why the V is ultimately going to be the less. That's why that block will be come down first instead of this disc. All right, let's say I have a, please guys try to understand this one. If you do not understand, raise your hand or raise your voice over here, because I cannot see you right now. When you are in the class, I can understand what you are doing. Right now I cannot see you, right? Where you are, I do not know actually. Are you in the bed or in your table or are you in the road?
no sir, in my table.
Table, all of you?
Yes, sir.
That's great.
Yes sir.
That's great. All right. Here is a case actually. I have a meter stick which has a 1 meter long, and it has a hinge over here so that it can be rotated. So that's mean somehow I can hold it over here, let's say by my hand, I hold it over here. When I release, that system will be comes to the downward, and it will be over here. It is fixed with a wall over here basically in that case. So it's going to be the strike that surface when it's over here if I release that system. Now the question is asks you over here at what velocity this meter stick is going to be the strike over here. At what velocity it will be. It's look like that. So let's say if you hold on your stick with the wall, when you release, it's going to be the rotate about that point actually. So that's why it will be strike that surface rotating about this point. This is actually your rotational point. I should mark it over here. This is actually a rotational point. It's rotating about this axis. So they ask you at what velocity it will be strike that surface. This is the question over here. So, all right. So I can write over here simply the energy conservation law. What I'll write, let's say initial energy must be equal to the final energy, right? So it will be converted to actually that potential energy must be going to be converted to this is kinetic energy. All right. So initially it has, you can write down the kinetic energy plus that potential energy must be kinetic energy final plus that potential energy final, right?
স্যার একটা কোশ্চেন ছিল
Sure.
স্যার পিওর রোলিং মোশনের ক্ষেত্রে কি এনার্জি কনজারভেশন ল মানা হয়?
Why not? Of course. If there is a conservative system, definitely that mechanical conservation energy will be conserved over there. If the total energy conserved, definitely conservation energy will be worked over there. You get my point?
জি স্যার, বুঝতে পারছি।
Alright, so let's say that right now when I hold it this stick over here, what is this kinetic energy initially? What should be its kinetic energy? Zero. That's very good. What should be its potential energy? Let's say I choose this is my reference level, or I consider this is my origin actually over here. Let's say this is my x-axis and this is my y-axis. Then what should be the potential energy? It should be also zero, right? You understand?
Yes, sir.
Once again, sir.
So potential energy would be also the zero. Then I can write zero would be basically over here. What should be the final kinetic energy? It would be only rotational kinetic energy, right? Half of I omega square. And it should be potential energy actually that I'll write that. Yes, is there any question?
Sir, can you explain the potential energy part?
So initial potential energy.
Yes, sir, initial potential energy.
So I choose, this is my actually that reference axis. This is my origin, right? So with respect to that point, the potential energy would be zero if you write down this formula mgh, since my h is zero over here, right?
Yes, sir, because they're on the same surface.
Yeah, so that's why the potential energy is zero. Now when it's going to be strike the surface over here, then I can say it has that rotational motion, so that's why I write down half of I omega square, and its potential energy mgh y. And why I have to find out what should be that y actually over here. Now if I write this one actually, so half of I omega square minus this should be actually, I'm supposed to write this would be, or I can write mg, what should be the y? Y actually how much distance is travel along to the vertical direction. Since this system has a center of mass actually the midpoint, right? And when it's come over here, this midpoint would be over here. Am I right? Then is
Yes, sir.
change of center of mass, actually this length, which would be basically minus L by 2. Can I say that
Sir.
one?
স্যার
Yes.
স্যার আবার একটু বলবেন, আমি ক্লিয়ার শোনা যায় না এই পার্টটা।
আচ্ছা ঠিক আছে। So one more thing actually, so it will be difficult, yeah, I know that, but if you do not understand, definitely raise your voice. So my point is over here, since when I release that system, its center of mass actually over here, definitely its center of mass would be actually the midpoint, we know that, because it's a uniform distribution of the mass I consider over here, which is 1 meter long. When I release, it is rotated and this point will be over here, right? Do you understand this one? If this come over
Yes, sir.
here, then this length would be basically, I know this is actually L by 2 from here to here, because the total length of the rod is L. If it is the center of mass, definitely that distance will be L by 2. But when I release that L by 2 center of mass come over here, I give the minus sign because this is my origin, is going to the downward direction. So that's why I say that it's a minus L by 2. Okay, does it make sense to you?
Yes, sir.
All right, that's great. So that's why I will say this y would be over here minus L by 2. Oh, Mahir Alam. So then look at this, I can find out this thing would be 0 actually, and this one I'm going to find out actually half of, what should be the moment of inertia for this rod? Can anyone tell me? Let's say this rod has a mass is m, it's a uniform distribution, mass is m, and the length is L. It is rotating about this point. What should be its moment of inertia? We talk about this thing in your class, right? In the last class probably. Can anyone tell me what should be that moment of inertia about this point? What is the moment of inertia? Let's say I'm going to give you actually the moment of inertia throughout the center of mass, because I give you that word, I will give you this moment of inertia for this system throughout the center of mass, 1 over 12 ml square. Now what should be the I over here? Or how I'm going to find that? This I will be 1 over 12 ml square. Should it be?
So 1/3 ml square.
1 by 3 ml square. Yeah, that's great. Because this is rotating one end. So then it should be 1/3 ml square. Right? And omega square minus, oh, I write on the bigger m, so no, it should be the smaller m, because it's this m actually. Let's say this is the small m, this mass. Let's say this is the small m, then this is going to be the basically mg L by 2, right? So then I can find out, look at these, it should be 1 over 6, or I can cancel out the half from there. So 1 over 6 ml square omega square must be actually mg L by 2. This 1 L you can cancel out from here. I can cancel out also this m, I can cancel out 1 L from there, and I can also cancel 2. So then I'll find out this omega square would be basically 3g divided by L. I have a 1 L over actually over here, so that's why I can say this omega should be root over g by L. Why I'm finding out this omega actually? Because I want to find out v actually omega r. using that formula. If I can find out omega, I'll be able to find out the v, because I am to find out due to that rotation at what velocity is going to be strike over here, which is actually I'm looking for the v. So I can find out the v if I can find out the omega. That's why I find out the omega over here. Now what should be that one? So v would be basically omega into r. What should be the r over here? What should be the value of r?
L by 2.
Only L, yes, exactly. It's L. So then I'll find out root over 3GL into that L. Don't cross this L over here. Or simply it should be, you can find out if you plug in those value actually. L is 1 meter, right? Because it's a meter stick which has a 1 meter long actually. If it is decent length, you can find out over here. So for this case, I will find out if it is a meter stick, that's mean 1 meter long, then I will plug in this is 3 into 9.8 into 1 into 1, which will give you actually this V is going to be 4.52 meter per second. So that's how actually you can find out at what velocity this meter stick is going to be strike at your wall. All right, is there any question over here? No question. How many of you? 26. Please give your attendance. Just write down your ID into that box, text box. What is that say there? Just write down your ID. Do it, hurry up right now. In the 1 minute actually, because is anyone left? ROV Alamin. You write down the 2 ID. Why? Which one is your? ROV?
Sir, ভুলে দুটো চলে গেছে।
No. ROV you write 22299058. Which one is your?
058, sir.
058. All right. So all right. Thank you. All right, let's go for the next topics. Right now I'm going to talk about basically that torque, which is actually twisting force, we say that. So let's say I have a system, anything actually, you can also consider that torque actually. Let's say this system can be moved about this point. So to move that one, what you did, you apply a force over here. Due to that force, the system is going to rotate about in that direction, right? Which is actually due to that force, the system will be rotate. So then it will create a torque actually. So that's why we say the torque is basically the twisting force. Now this torque actually we can find out by a formula which we write the torque tau would be basically that R cross F. Torque is a vector, remember, it has direction. These are actually the distance from your rotational point to your applied force. For this case I can say this distance is basically R over here. And it's a cross product, definitely it has the direction. You know how to find out the direction of a torque using the cross product, which is you required actually that right hand rule, you know how to use that right hand rule. You can find out using that one. Sometime if you want to find out that magnitude, you can write down this would be r f sine theta, right? But theta is the angle between your vector r and f. Let's say sometime I will find out the situation in a case, instead of applying the force over here, I can also apply the force over here. Due to that force, it will also rotate. So let's say about this point. In that case, what we are going to say, this is my r, right? This is the r. So then in that case, I have to find out what is this basically, that theta. Theta would be basically this one. This is the theta, which if we extend this part, this is actually the same angle over here, which is, we say that theta is the angle between your r and theta. Do not consider theta would be this one. This is not. This is actually that part. And if you ask me then why this system is rotating, then I will say this system will be rotate about this component of this force. I know if you create the angle over here, you will find out one component in this direction, which is f cosine theta. Another component is f sine theta, this angle, right? In that case, this system will be rotated about this force, which is f sine theta. This f sine theta will be responsible to rotate this system. You can give the example for this torque actually when you pull a door of a room, because that door you apply a force to open the door in one side, and the door is rotated about the other side of this axis, right? Or by a hinge actually, this system will be rotated. So that's why we say that the torque is very important. In a sense, 3 point is very important. The first one actually, that at which, not the 3, is the 2 basically, where you are applying the force, which is means the r, and which direction actually you are applying that force. Depending on these 2 points, actually the torque depend on the system. Because if you apply the force in that direction solely, will that system is going to be rotate? Let's say if I apply the force in this direction, will the system will be rotate about this point? The system is not going to rotate, because angle in that case basically that 0 with that, right? If you plug in this angle is 0, so sine 0 is 0, then I can say the torque is 0 over here. So that's why the system is not going to rotate over here. So even though if you apply the force over here, let's say if I apply the force over here, will the system will be rotate? It is not also going to rotate. In that case, your r is 0, right? So that's why we can say the torque will be also the 0 over here. So that's why it is important when you are going to rotate a system, you have to check that which direction you are applying the force and where you are applying the force. Depending on these 2 points, actually the system will be try to rotate. And to rotate, definitely you have to apply a force in such a way that it would be easier for you.
স্যার আবার একটু বলবেন জিরো কেন হবে?
In both situation,
মানে টর্কটা জিরো কেন হবে?
acha, okay, fine, I got your point. So I say torque would be 0. Let's say if I apply the force in that direction, right? So if I apply the force in toward that direction, then what is the angle between your r and the f? Your r is that direction and f is also that direction, right? Then what will be the angle?
Yes, sir.
What is the angle?
Zero.
Angle is 0, right? If the angle is 0, sine 0 is 0, then the torque would be 0. For this case, I say. Second case, I say if I apply the force over here at that rotational axis, if I apply the torque is over here at the point, the rotational axis, then r is 0, right? R is 0.
Yes, sir.
Then torque will be also the 0. In the 2 situation, I say if you angle is 0, then the torque is 0. If the r is 0, then definitely the torque will be 0. According to this equation I write down over here. Alright, fine. Let's go forward. Let's say I have 2 objects. Initially basically the object is over here. let's say this is M2 and this is M1. So I apply a force over here, which is F. Due to that force is travel a distance. This is the new position of M1 and this is the new position is M2. It's created some angular displacement which is del theta over here. As well as you can say that this is a linear displacement which is actually that S. I want to make a relation between that torque and angular acceleration over here. So that's why I write down this thing. Try to understand what I'm doing over here. If I apply that force and due to that force is make a angular displacement or as well as the linear displacement, then I can say there will be some work done. That work done should be del W should be F into S, which is simply be change of kinetic energy. Right? Can you write this one? Fine. So right now over here that this change, I'll be write down this equation simply del W should be F into S. Why? Look at this, your force and the displacement are in the same direction in every point. So that's why the angle is 0. If the angle is 0, then the dot product which is F dot S would be F dot cosine theta. So theta would be 0. So cos 0 is basically the 1. I can write down it should be simply Fs. Now this is, I can also find out, let's say this is actually distance is r, then I can write down from a definition S over r should be actually the del theta. Can I write this definition? Arc divided by radius should be basically that this angle is going to be created over here. I use the definition over here. Then I can say from this one S should be r into del theta, right? I'm going to write down this thing over here. So then I'll simply write down this del W would be F, instead of S I'll write down r into del theta, right? Let's keep it at that. I'll use this thing. Now I can write, say that work energy theorem actually I will write down, let's say change of kinetic energy for this case simply would be half of I omega F square, that is actually that my final kinetic energy because it's rotating, that's why it has only rotational kinetic energy, minus half of I omega I square, right? Final, this is the final kinetic energy, this is the initial kinetic energy. I'm writing those things over here. That should be del K. I can factor out this quantity, half of I, it should be omega F square minus omega I square, right? Now I'm supposed to write this thing could be written in the way actually del K half of I omega F square minus omega I square. I'll be able to write down this thing would be basically twice alpha into del theta. How? If you ask me, then you have a formula omega F square actually omega I square plus 2 alpha into del theta, right? There is a formula we write down for that rotational kinetic energy. It's the same v square equal to u square plus 2ax. Right now for the rotational case we are writing in terms of angular velocity omega F square equal to omega I square plus 2 alpha into del theta. Fine. So I replace that one. So that's mean omega F square minus omega I square will be simply 2 alpha into del theta. Alright. Let's write down this del K. I can also write down this one actually because this is that work done actually change of kinetic energy. I'm going to plug in instead of del K, I'll write down this one F into R into del theta. So I'll write down in the left hand side it will be F into R into del theta from the equation actually. This one I'm writing. Then in the right hand side I can write this half will be cancelled out. I'll find out I alpha into del theta. This del theta I also cancel out from here. Then I will find out Fr actually that I alpha. Now what is the Fr? This Fr actually over here is the definition of torque, right? Because look at this, I have a system over here. So I apply a force onto that object F at a distance is R. So definitely this is actually the torque. And its angle is 90 degree right now for this case. In this situation, the angle is 90 degree. If we consider in general case, then I can say this is actually the torque. That's why I write down the torque would be basically that I alpha, which is analogous to the F equal to ma, right? F equal to ma. I said you in the case of rotational motion, m is analogous to the I, which is moment of inertia, and a is analogous to that alpha, which is actually, we say that this is also, I say that torque is actually the twisting force. That's why this is also known that as a Newton's second law in terms of angular version. This torque actually that I alpha. Sometime you will find out, we write down the net torque system would be basically that I alpha. Remember this equation, this is a very important part actually for this case, this equation. Is there any question over here? No question. Alright, let's talk about that angular momentum. We talk about the linear momentum. Right now angular momentum, let's say you have a object, any arbitrary shape of object, which is rotating about this axis at a angular velocity omega. Let's say this is, who is knocking me right now? Khan Imran. Alright, so this is rotating about this axis, and I know there is a, let's say there is a point mass over here which is also be rotated, right? Which we, let's say this is the mass of this object actually, that mi, this object, which is the point mass at a distance actually, let's say this is the r, or I can say this is the ri, then it has also the speed to that direction, which is the vi. Then angular momentum for this point mass mi, I can write down, it is simply L should be ri cross pi. Simply that angular momentum for a point mass, we can define actually r should be basically L cross p, because wire, that's it's a linear momentum, right? P is actually the linear momentum. System has a mass, p actually m into v. So that's how actually we define that angular momentum for a point mass distribution. So if you have a point mass which is m with a speed v, then its angular momentum actually will be r cross p. R actually the distance from your rotational axis to that location of that point mass, and p actually the linear momentum of that system. Since I choose only one mass, which is, I am saying that mi, so that's why I use the index I over here. You can use the different index if you want. So I want to, why I am doing that, I want to find out the total angular momentum for this rigid body or this object actually. What I can write over here, let's say I can write down this Li should be over here r cross p should be mi vi, right? I can write down this one, and I can write this one. Look at this, I can factor out this mi over here, this mi, so ri cross vi. Can I write? Now can you tell me what is the angle between this ri and the vi? What is the angle between the ri and the vi?
90 degree.
90 degree, exactly. Remember this point, because this is the point mass is rotating in that direction, is a circular track. Then every point, this velocity will be tangential to the path, right? It means that it will be always create the angle 90 degree with the radius. Whatever the position, it doesn't care about. That angle will be always actually the 90 degree. So that's why this should be 90 degree over here. And sine 90 actually the 1, I will simply write down the magnitude in that case. Li should be mi into ri into vi, right? Now this vi I can write down actually again omega into r, because it's rotating about a angular velocity omega, I say. Then I will simply replace by that part, which L should be mi ri vi, instead of I will write down omega ri. Then I can simply write down this Li is going to be mi omega into ri square, right? Or simply I can write this Li, if you rearrange this part, omega into mi into ri square, which is actually that angular momentum for this point mass. Let's say if you want to find out for total or this whole object, I will simply basically summation all the point. I can write down this total angular momentum for this system will be summation of I1 to n. If the system has a n particle, then I can write in this way, right? Because I find out only for one point mass the angular momentum of this one. If I want to find out for whole mass, and if it has a nth particle, I can add them together to find out the total angular momentum. Let's plug in those value over here. It's a 1 to n. It should be omega mi ri square. I can factor out this omega because it is constant, then I can write down 1 to n mi ri square. Now what is that mi ri square? What will be this thing?
It will be similar.
Moment of inertia.
Moment of inertia. So
Huh?
that's why I write
Moment
down
of inertia.
it's a L actually that I omega. This is that angular momentum of this system. And this is we write down when the system has a moment of inertia I and rotating angular momentum omega. This would be the actually the angular momentum. For the point mass distribution, we can write down, there is two formula actually to write down that angular momentum. If you know that linear momentum, you can use this formula, or if you do not know that linear velocity, if you know the angular velocity, you can use that formula to find out that angular momentum of the system. That's how actually we find out that angular momentum for these two cases. How many minutes do I have? How many minutes do I have?
Three.
3 minutes?
3 minutes.
3 minutes?
Yes, sir.
Alright, so I do not want to start then in that case of the new topics. Do you have any question?
স্যার আমাদের বলছিলেন কুইজ নেবেন
Yeah, that's point. That's a very good point. Thank you very much.
কবে
Is probably I announced that in the Tuesday, right?
Yes, sir.
The Tuesday,
Yes, sir.
and that should be after 10 p.m. actually.
Yes, sir. You said 10 to 10:30.
Yeah, 10 to 10:30 is it okay, or is there any issue?
Sir.
No.
সাড়ে দশটায় দিন স্যার দশটায় না স্যার
Yes, I know. It's not be the 10. It should be the. Can I give it that 11? Because if I fix it the 10, there is the issue for Tarawih namaz. All right.
Yes, sir.
Okay, sir.
Yes, sir.
Sir, no problem.
I think it should be better if I fix it 11 to 11:30. I will start exactly at the 11. It will be ended within 11:20 because it's not required more than 20 minutes.
Okay, sir.
অ্যানাউন্সমেন্ট করা হয়েছে স্যার
So then we are going. Your quiz is going to be that Tuesday at 11 a.m. and your topic is only the linear momentum, right? Linear momentum and the pollution.
ওকে স্যার
All right. So then, fine. Thank you very much. We are going to meet in the next Tuesday again. That's with the last class before the vacation. All right, guys. And one more thing, guys. Please do not go to the outside in this high temperature. It's a really terrible situation. I do not know what will happen actually. So it's a very tough situation. Please take care of yourself because right now, after the vacation your final exam is coming ahead, so that's why it's a very crucial time for you. Please take care of yourself. All right, guys, thank you very much. See you in the next Tuesday. And one more thing, actually, you can use the same link, actually. I will also post that before the class, actually, in the Slack. I'll use the same link for these classes, online classes. All right?
স্যার কুইজের সিলেবাস কি?
It's only that linear momentum and collision.
ওকে।
All right, guys, thank you very much. See you in the next class.
আসসালামু আলাইকুম স্যার।
From Assalam.
আসসালামু আলাইকুম স্যার।
আসসালামু আলাইকুম স্যার।